Surface tension is the tension of the surface film of a liquid caused by the attraction of particles in the surface layer by the bulk of the liquid, which tends to minimize the surface layer. These cohesive forces between molecules cause a skin, or film, on the surface of the liquid. In water, the attraction is facilitated through weak hydrogen bonds. The surface tension of water provides the necessary wall tension for the formation of droplets, as the spherical shape minimizes the wall tension needed for the surface layer, according to Laplace's law. This law says that the larger the vessel radius, the larger the wall tension required to withstand a given internal fluid pressure. One cool application of this is raindrops. We have the idea that raindrops have a teardrop shape, but where does this come from? Raindrops are shown like this everywhere, from movies to books to the Weather Channel. What if I told you this is wrong? The shape of a raindrop while falling depends on the size of the drop and the balance between surface tension forces and the air pressure the drop is subjected to. As we already discussed, surface tension is caused by the attraction between the liquid particles in the surface layer. It acts like a skin, caused by the molecules sticking together due to weak hydrogen bonds. Air pressure is caused by the air resistance to the falling motion of the particle and is represented by 1/2 times the density times the velocity squared times the reference area on which a drag coefficient is based. Raindrops begin high in the atmosphere in a spherical shape due to surface tension. Then, as they fall, the air pressure flattens them out to resemble the shape of a hamburger bun. There is a greater airflow on the bottom of the drop than at the top, so the surface tension dominates on the top and stays spherical while the bottom flattens out. A video released by NASA in 2014 revealed the true shape of a raindrop. As the raindrop falls and collides with other raindrops, it gets larger. Eventually, it becomes too large and breaks apart when the surface tension is overcome. Utilizing this technology allows meteorologists to estimate the vertical and horizontal size of raindrops in a storm, which can be used to predict the intensity of a rain event. Flatter and wider drops signal heavier precipitation. Some radars in space can actually measure the size of the individual drops. We began this video by applying the principles of surface tension, and now we understand why the shape of the raindrop is what it is. And this understanding can actually give us an insight to global rainfall states and trends.